Hi. I'm going to go over these notes quickly for work, energy, and power. So, as I was saying before, work is under the symbol W is the energy transferred when a force F is applied to an object moving through a distance D. So we have work is equal to the parallel force times distance. So think about that as, something moving across a plane. Work is only done by the force, the component of force parallel to the distance the object moves. So let's say um, you have a car pushing another car. Okay, so that would be work. All right along that same plane. So the SI unit of work or energy is the joule, which is J, and 1 joule is equal to 1 Newton times meters. So a student lifts a 50-pound ball 4 feet in 5 seconds. How many joules of work did the student complete? So we have W equals F times D. We have 50 times 4 is 200 foot pounds. This is the amount of work, but it is not in the SI unit of joules. So we have to do a little conversion here. So we're going to convert 50 pounds to newtons. And so that is 1 Newton to 0.225 pounds gives us 222.5 newtons. And then 1 meter is 3.28. So we have feet. So 4 feet is equal to 1.22 meters. Thus, we have um, a total of 271 joules. The ability to do work, right? So, light, heat, mechanical, chemical, and electrical forms of energy can all be used to exert a force for distance. Excuse me, I'm fighting a cold here. Here we see roller coaster and um, NASA solar sail, which is pretty amazing stuff. And then we have fuel cells. So potential energy um, is stored energy, right? So it's the capacity to do work by virtue of position or configuration. So think of pulling back a rubber band, and that is the potential energy. The energy of releasing is called kinetic, right? So we have um, kinetic energy, energy which a body possesses because of its motion, which occurs anywhere from an atomic level to that of a whole organism. So here we have chemical versus kinetic, radiant versus chemical, and electrical versus thermal energy transfers. Okay. Renewable energy sources, biomass, hydropower, geothermal. We went over these previously, wind and solar. I'm a big fan of hydro power. If I had the capacity to to take a class trip, we would go to the hydroelectric power plant in Niagara Falls, which is amazing, totally amazing. So here we have coal, natural gas, petroleum, uranium. These are non renewable energy sources. Okay, so um, energy cannot be created or destroyed, but it can change can change from one form to another, which is pretty mind blowing when you think about it. Energy cannot be created or destroyed. Energy lost to heat when an input energy is changed to an output energy. So some of the output is usually heat energy. And sorry, my battery is running down. So think of a car engine, and the exhaust would be the heat that comes through. So here we have examples of energy conversions for making electricity. We have fossil fuels where it's chemical, heat, mechanical, electrical. Um, Solar is sunlight that turns that into electrical. Um, and So with wind turbines, we have the kinetic energy, uh, which in turn makes it mechanical, which in turn turns it into electrical. And hydroelectric is gravitational potential and turning the turbines mechanical, and and so on. And that's what we have. So vehicle system conversion, mechanical, comes from chemical and mechanical. Which output is desired, mechanical or heat? All right, now we get into efficiency. Okay, and this is the percentage of the input energy E in that is transformed to the output energy in the desired form E out. So efficiency is usually written as a percentage E out over E in times 100%. E out over E in. Okay, so what are current energy concerns? Obviously, pollution, depletion, dependency, and cost. You can see that our consumption, although this is probably a little older, um, we are still way too dependent on petroleum, natural gas, and coal. Not as much coal, but it is, and um, that needs to change. Not only for pollution considerations. I am an engineer, and using 19th century technology just is not adequate for me. So power is the rate at which energy E is expanded or work W is performed in time T. So therefore, we have P is equal to E divided by T, or P is equal to work divided by T, or time. Okay, so the SI unit for power is the watt, and 1 watt is equal to 1 joule per second. So here we have uses electrical energy to do work, mechanical uses mechanical energy to do work, linear or rotary, and fluid power uses energy transferred by liquids and gases. So, how many watts of power did the student use to lift the ball? So, it was 271 from the earlier slide joules. And over time, which was 5 seconds, right? So, it becomes 54.3 joules per second, which in turn is equal to 54.3 watts. All right. So that's where we have for power. is in watts. And that's that.